Hello everyone, my name is Arya Mazaheri, a researcher at Technical University of Darmstadt. Together with my colleagues, we would like to introduce you to our research on acceleration of Winograd convolutions. Deep learning is the art of creating machines that perform functions which require intelligence when performed by people. I think you all agree that deep neural networks are being used every day nowadays to detect objects, performing translations, composing musics, and even playing with the human. Convolution neural networks are a specific type of deep neural networks that they try to learn to transform input data such as images into successive layers of increasingly meaningful and complex representations. So whenever we try to traverse from the beginning layers to the layers at the end, we can notice that those layers at the end try to represent more coarse-grained information, and that's how convolution neural network usually perceive the world. One of the most important layers available within these networks is actually the convolution layer, and the convolution is nothing more than a blending of two functions into a third function. We have the input tensor and the kernel tensor, and the job is to convolve the kernel across the input by performing element-wise multiplication and doing a summation right after that, and we just need to store the result into the output tensor. Convolutions usually dominate more than 90% of the total runtime, and it means that we have to find a way to parallelize them and gain more efficiency. Thankfully, they are similar to matrix-matrix multiplication, and GPUs are a good fit for exploiting massive parallelization. One way to implement a convolution is to use Winograd algorithm. Winograd algorithm is a method which can reduce the number of arithmetic operations within a convolution. And the way it works is that we first start with a tile, and we have to transform both the input and the filter into another space. So by performing matrix multiplication among the transformation matrix and the input or the kernel, we can transform both the input and the filter into another space. After getting the results, we just need to perform a multiplication. It's an element-wise multiplication, and then once we get the results, we need to transform the result back into the original space and store it into our given output tensor. The research questions that we had for this paper is that, is there any way to reduce the overhead of Winograd transformations? As you can see, we had to perform 6 multiplications in order to transform the matrices into the desired space. Is there any way to properly choose the right internal tile size for the Winograd? Because it really affects the accuracy of the computation and also the speed. Is there any way to use a single code while being able to run it on a wide range of GPU platforms and also get acceptable accuracy and also efficiency? So these are the questions that we would like to answer in this project. The way that we address these questions is that we first try to implement our approach in an inference framework, and the way the inference framework usually works is that it tries to represent the neural network as a computational graph. So we take the computational graph, we try to select the right variant. For example, the auto-tuner might try to select a Winograd convolution, and if a Winograd is being selected, then our job is to generate efficient transformation recipes. Then the code generation tries to use a template. We have a template for non-fused implementation and fused Winograd implementation. The fused version is usually preferable over the non-fused one because it tries to merge all those steps within the Winograd into a single kernel so that we save some time and memory. The code generation tries to fill in those placeholders by the right instructions, and at the end we get programs written in CUDA, OpenCL, and Vulkan so that we can target various GPU platforms. We try to use symbolic analysis for performing optimizations. As you saw, performing Winograd transformation requires us to run a matrix multiplication, which is similar to this code with 3 nested for loops. And this is really costly, especially when you have 6 of these for convolving each tile. The good news is that the transformation matrices for a given Winograd convolution are always the same and often follow a regular pattern. Therefore, we can avoid running an ordinary matrix multiplication kernel, and instead we use symbolic computation to intensively simplify the transformation steps into a sequence of instructions for constructing the transform matrices. The first optimization is that we simply try to remove zeros and 1 so that we can avoid multiplying by 1 or 0 and also addition with zeros. So we simply get the symbol or the 0 if necessary. The second one is that we try to transform the resulting matrix into a vector with the variable subscripts replaced by an induction variable symbol. The ultimate goal here is to generate the transform matrix using only a single loop construct. The third optimization is that in the case we find common coefficients across the terms, we apply factorization to save redundant multiplications. And the last but not least is that we use common sub-expression elimination algorithm to find the common terms among the vector rows. Therefore, we can simply compute them once and reuse them multiple times. So here is the result after performing all those optimizations. Previously, we had to perform these nested loops, and here we only have a single loop, which is much more efficient, and we can also unroll the loop if necessary. It is generally difficult, even with metaprogramming, to write code that runs well across more than a limited range of input sizes. Therefore, we use auto-tuning to tune Winograd parameters as listed here. So we can tune Winograd variants. It means selecting between fuse or the non-fuse one. We can change the thread blocking factor, register blocking. We can unroll the loops to a factor that we want, or the auto-tuner selects. And the Winograd output tile size can be selected by the auto-tuner as well. Moving toward a larger Winograd internal tile size, as I said, leads to a higher accuracy loss. Therefore, we observe that the error rates increase for larger convolutions. However, it does not precisely follow an exponential trajectory, as other researchers previously mentioned. We notice that Winograd convolutions, even with even alpha, benefit from a lower error growth rate. Specifically, the lowest error growth is when alpha is equal to 8. To demonstrate the effectiveness of our method, we numerically analyze the computations involved in Winograd transformation steps by directly counting the number of additions and multiplications. We observed that our method was able to reduce the number of arithmetic operations in transformation steps by up to 62%. We often obtain the highest amount of reduction when alpha is equal to 8. Such a value for alpha, or the internal tile size, enables our method to factorize more common terms and improve data reuse. This is also true for runtime and the GPU. Overall, our analysis of both accuracy and the number of arithmetic operations in Winograd transformations after optimization confirms that when alpha is equal to 8, Winograd convolution can be optimized to a greater extent. So here we try to analyze the performance portability of our approach. We analyze the performance portability on various GPUs. Here you can see the results for NVIDIA 1080 Ti compared to also including the QDNN vendor library. The results reveal that not only our method can yield runtimes close to QDNN performance, but can also perform better than QDNN by up to 8.1 times in some cases. However, QDNN can achieve better runtimes for larger convolutions, and we think that this is mainly attributed to more efficient matrix multiplication routines. Here again we try to assess the performance portability, but here on AMD GPU it's RX 580, and in specific cases we were able to outperform AMD library to a factor of 1.9. So we analyzed the performance portability on mobile GPUs as well. This platform, which is a Mali G71 GPU, is entirely different from the previous two GPUs and usually requires an enormous amount of effort to achieve reasonable performance. So here we show the results of using the autotuner to select the right Winograd implementation and tuning parameters. When autotuning is enabled, we can achieve a considerable speed up on average by a factor of 1.7. Autotuning enabled us to find more efficient implementations and even surpass the performance of the ARM compute library for several convolution operations, as you can see on the diagram. So, to conclude my talk, we use symbolic analysis to optimize the Winograd transformations, and we use the metaprogramming and code generation to enhance the performance portability of Winograd convolutions. We realized during this project that efficient Winograd convolution is really tricky to implement, and when alpha is equal to 8, when the internal tile size of the Winograd is equal to 8, we can achieve the largest arithmetic reduction with acceptable accuracy loss. And the last but not least, performance portability and 3 different architectures have been evaluated. We evaluated the performance on the NVIDIA, AMD, and also in a mobile GPU, and we realized that we can get acceptable performance and we can actually achieve performance portability compared to vendor libraries. So if you have any questions, please feel free to contact me via this email, and I wish you a great day. Thank you.